Okay, so now we have a C statement that involves memory. We have 3 instructions beyond this, but what I want to do is concentrate on what a C compiler will do when you issue these 2 initial statements. So, when you say int a of 5, you are declaring a 32-bit integer array, 5 integers long. So, what that's going to do is allocate 20 bytes. There will be 20 bytes in memory associated with array A. Now when we say int b equals 1,000, what we're going to do is allocate 1,000 32-bit signed integers. That's going to be 4,000 bytes. So I have to give you the address in memory associated with the base of A and the base of B. So the compiler would usually make that decision, but because I am Lord and Commander, I get to tell you that A is going to be associated with register 9. Now, B, I'm going to write this a little bit differently. A is an array. Now when I say A of 0, I mean the 0th element of array. I'm going to say that A bracket bracket, which means that the array A is going to be associated with R9. Then the array B, remember A has 5 elements, B has 1,000 elements, doesn't matter, it's going to have a base. And 5 ints are going to be allocated at the base of A. 1,000 ints are going to be allocated at the memory associated with B. 1,000 ints, 4,000 bytes. All right, where does B start? Well, the compiler has to tell it, and I dictate that we're going to have it in R18. So, this means that R9 contains the address of A of 0. So whatever number gets put into 9, which will be an address, which will be a 32-bit unsigned address, is going to be the first byte of A0. So R9 plus 1 contains the second byte of int A0. R9 plus 2 is going to be the third byte, and R9 plus 3 is going to be the last byte. Okay? So, if we were to go to R9 plus 4, so R9 is A of 0 byte 1, R9 plus 1 is A0 byte 2, R9 plus 2 is the third byte of the integer A0, and R9 plus 3 is the last byte of the 32-bit or 4-byte integer A of 0. Okay? So R9 contains the base. R18 contains the address in memory of B of 0. We're ready to go. Now, I'm going to issue some instructions that use the arrays A and B. Let's say that B of 7 is going to be equal to A of 3. This involves 2 steps. It involves reading A of 3, and it involves storing into B of 7. And then since this is a C statement, it has a little semicolon. Don't make me start about my joke about semicolons. The next C instruction we have is that A0 is equal to B of 1. And then finally, we have B of 9 is equal to A of 1 plus B of 100. Now, A only has 5 elements. We can go from A0 to A4. If we were to go to A bracket 5 bracket, we would have a memory fault. So notice A3, A0, A1, we are all still within that 5 int range. But B is much larger. So I can say B of 100 because B has 1,000 elements. Were I to say B bracket 1,000 bracket, it would be a memory fault because we start at 0 and the largest reference we can have to B is B of 999. All right, so now we need to turn all this into MIPS statements. Now we cannot do this directly. We have one instruction, load word, that drives from memory. We have one instruction, store word, that puts into memory. So we're going to need to use temporary registers to store. We're going to need a temporary register to suck in the data, have it as a temporary register. Then we're going to use that register to store back into memory. Here, for the first instruction, we're going to use a temporary register to read A3, first instruction. Then the next instruction is going to be to write or store word into B of 7. Let's begin. Now, I'm going to say that R10 through R14 are trash registers or temporary registers. So I can clobber these registers with impunity. All right. First, we need to load A3 into a register. So we're going to do load word. Now, the first argument, or the first thing that appears, is the destination. I'm going to choose my trash register, register 11. Then I am going to put into register 11 the base of A, but it needs to be offset, not by 3 bytes, but by 12 bytes. So, what we're going to do is we're going to have the offset. I'm going to write that down. Remember, the constant offset comes first, and then we're going to have a register. So the offset is how many bytes forward from the base of A we're going to need. Base A starts at 9, register 9. But we don't want to put a 0 here because that would be A of 0. We don't want to put 4 here because that's A of 1. We don't want to put 8 here because that's A of 2. What we want is A of 3. A of 3 is 12 bytes beyond A of 0. So we've got A of 0, A of 1, A of 2. We want A of 3. So we're going to put 12 here. Now 12 is a constant, not a register. That is A of 3. What we've done is we've taken the base of the array stored in A9, we've added 12 to it, then we've went out to memory. We've grabbed the payload. Now we're taking that payload, not the address, but the payload, whatever was in memory at address 9 plus 12, and we're putting it into register 11. Now we don't have to do anything with it, we just have to store it back. So we're going to do store word 11. Tricky, tricky, tricky. This is actually an argument when we deal with store word. Store word 11. Now where do we want to put that back? We want to put it back in B of 7. We don't want 7 bytes beyond B. We want 7 words beyond B. So we're going to multiply the 7 by 4. It's going to be the value 28. But some of you, I'm thinking of you, Danny, are going to have to take off your shoes because 4 times 7 is 28, and you're going to run out of fingers and toes. Okay? Some of you may use your little toy TI calculators, and by some stretch of the imagination, a TI calculator can handle 7 times 4. Why do we multiply 7 times 4? Because it's the number of bytes. Each word is 4 bytes. So, here we have store word 11, the argument, whatever is in 11, which was the payload from memory. Store word, using source 11, we want to go 28 bytes beyond. And then what is our base of B? Well, our base of B is register 18. So we put cache 18 here. And these 2 instructions implement the 1C line that we are to implement. Next, A of 0 equals B of 1. Well, we're going to have to load from B into A. So we've got the load word. Now, trash register, I get R10, 11, 12, 13, and 14. Let's choose 12. 12 is going to be a trash register. Now we want to access B of 1. B of 1 is 4 bytes beyond the base of B, so we're going to have 4. 4 is the constant. Now we have, and I forgot to mention, these have parentheses around them according to the MIPS assembly language. So 4, then the register. Now we want to read from B. B's address is in 18. So it's not what's in 18. 18 is used as an address. The address stored in 18 plus 4, we go out to memory. We have an address. There's a 4-byte, 32-bit signed integer in whatever address is register 18's contents plus 4. Okay, so 18 to the floor, we go out to memory, we find a payload, we shove it into 12. Now, we need to store. What do we want to use as an argument? Well, A0, or B1, was loaded into 12. Now, that's not B1, that's the memory contents at B1, which we've loaded into 12. So 12 now becomes an argument. And where do we want to put it? Back in A of 0. Well, A of 0 is the unadulterated address, R9. So we put in 9 here. Next, holy cow, we've got 2 elements that we need to shove into B9. That means we're going to need 2 temporary registers. So we're going to load both of them. B of 100 is going to be the address base R18 plus not 100 but 400. We're going to need to choose a trash register. Which trash register do we want? Oh, I heard R10. So R10 is going to be the trash register, and we want to put B of 100 in it, so we need 400 bytes. Then, what is the base of B? That's in 18. Next, we're going to need to load another one. Trash register. We can't clobber 10 because we need it. Let's use 11 as a trash register. We want A of 1. That's going to be 4 bytes. Then, what is the base of A? The base of A is in R9. Now, we've got 2 registers, 10 and 11, which contain B100 and B and A of 1 respectively. We're going to have to do an add command. Add. Now, we could choose 10 or 11, But let's go ahead and choose 14 as our trash register. I like to throw my trash all over the place. So, I'm going to add these together. 10, that's a cache 10, and a cache 11. Add these two together. What that gives us is the sum of those two memory payloads. Now, we need to store it back. We're going to store it back into B of 9. So we have our sum in R14. So we're going to use R14 as our value to store back into memory. Where do we want to go? 9? No. 4 times 9, because it's 4 bytes times 9. 9 is the number of 32-bit signed integers. So we're going to need 9 times 4. That's 36. 36! 9 times 4. Then we're going to store it into the 36 bytes beyond the address of B, which is 18. 18. Thank you.